So this is 141, cryptography. This is the second class meeting. One thing that I didn't have on this page yesterday was the link for non-CCSF students to use to turn in homework and stuff, but now it's up. It's here. So you can use that to turn in homework and participate in discussions and so on. And I think that's about it. If anybody wants to add, I added everybody earlier today, so you should all be in if you want to be in. And let me know if anybody has any troubles. But anyway, let's see. There's nothing in the Zoom chat. Good, nobody in the Zoom. All the action is in Twitch, which is where it should be. All right, so let's talk about the first lecture, which I have to open again. Well, it's the first chapter. It's technically the second lecture anyway. There we are. So here we are, the basics of encryption, to get us off to a start here. I think that'll do. All right, so we're going to talk about the basics. I wonder if every slide is going to have that line in it. Oh, good, the line went away. Good. All right, so we'll talk about classical ciphers, which are the old-fashioned ones which are no longer considered secure, but they're important to understand because they form the basis of all modern ciphers. They're all just variations on the old ones. And the perfect encryption, the one-time pad. Let me make this zoom to fit. There we go. It is something I was a little surprised to find out. There's been perfect encryption known for about a century or two. Never been broken, probably never will be broken. It's just kind of irritating to use. And so then we'll talk about how you measure security and how things can go wrong. So here's the basics, basic context. You start with plain text, which is some kind of unencrypted message. Then you encrypt it with a key, and then you get ciphertext. And the idea is somebody who tries to read the ciphertext can't read it. But the person who is authorized to read it has the key and a decryption routine, so they can take the ciphertext and decrypt it to get back to the plain text. And that's standard classical private key encryption, which is the only kind of encryption that existed for anybody outside the military until 1979, when public key encryption became publicly known, which is the alternative. But everything in this lecture is the old-fashioned private key encryption, which is what most people use for most purposes. So the classical ciphers, this was military strength encryption 2,500 years ago. You would take a message like Caesar and you would just move every letter forward a couple in the alphabet. So C would go D, E, F, A would go B, C, D, and so on. So you'd write this message, and in an era when most people could not read at all, even a small amount of scrambling like this was enough to make it very unlikely that anybody would figure out how to read this without having the Captain Crunch decoder ring at the other end, which is, when I was a kid, you'd get this in a box of cereal or snacks, a little wheel that spun on another, and the Confederate Army used it also the same way. They had a little brass, you'd carry around this wheel that you could turn a few steps to move everything forward a few letters in the alphabet. So you can do that in Python, and Python is the main tool we'll use in this class to do these simple encryptions. It's a very good way to learn. Python is so easy to use that you don't actually have to know hardly any coding to do it. So it's pretty much like the language I started with, BASIC, where you can just sort of read the code pretty directly. So if we do nano Caesar 1, all right, so here I define the letters, which are just all the capital letters in order. Now I read the plain text from the user. That's what this does. It takes input from the user, prints plain text, and whatever they type in goes in this variable plain text. Then I ask for a shift number, and then for every character in the plain text, I find the letter in this, and then move it forward by the shift. But if it goes off the end by getting longer than the length of letters, then I move it back by the length of the letters list, so it wraps around. And that's it. So yes, Python can be hard to install. If you're putting it on Windows, it's pretty miserable. But there's online sandboxes you can use. And on Linux and the Mac, it's already there and it's easy. Anyway, so I can run this thing. That's Python 3. So Python 3 Caesar, if Caesar 1. All right. So if I put in hello and I shift it by 1, it turns into IFMMP, moving every letter forward 1 and so on. So that's the joy of the Caesar cipher. Now, we can do a brute force attack. So let's take a look at that. All right, all this does is it has the same stuff, but it only asks for the ciphertext. It doesn't ask for the shift. Instead, it tries every shift possible in the range of letters and just prints them all out. So if I take this one here, IFMMP, that's ciphertext, and I gotta copy it. All right, and now I take, I just wanted to make it bigger. All right, and now I run that, Python 3 Caesar 2. I feed in my encrypted text. It just prints out with every shift. So you just look down here until you find the one you can read, and that's the decrypted text. This shows the essential stuff. There's a couple things that this is a simple example, but it might not be obvious. The fundamental problem here, of course, is there are not enough keys. You can try every key. Another problem, which might not be as obvious, is that if you have the wrong key, you get gibberish. If there were multiple keys that created a readable message, multiple key values, then I wouldn't be able to tell which one was real. But for most ciphers, they have this property, almost all the ciphers we use these days, in fact, I cannot think of any exceptions, that if you have the wrong key, you just get nonsense. So all you have to do is look for anything that makes any sense, and then you know you've found the right key. All right. And then there's the frequency attack. Let's try that. I think that's got to be Caesar 3. All right, I don't see why the Caesar 3 is there. Let me check my slides. All right, we'll get to that later. All right, so this is the brute force attack where you try every possible key. So now to avoid that sort of thing, the Vigenere cipher, who I think is French and therefore I'm sure I'm pronouncing his name wrong, had this. You would have a key that is a few letters, like they drink the tea. And then you repeat that over and over. They drink the tea, they drink the tea, and this would be used to tell you how far to shift it. You would shift it by the numerical value of t, shift this by h, shift this by e. So each letter would get shifted by a different amount. And if the message was shorter than the key, there'd be no pattern at all, but if it's longer than the key, which is the normal situation, then there will be repetition at the size of the key. And it can be broken, but it's much more difficult because you won't see a simple pattern. And here, for example, is a fake pattern. I thought it was good when I made this slide, but I noticed when reviewing it, it's not. This "the" will have the same pattern of shifts as that "the," but this is they drink the tea, so it's not going to be evenly spaced. The real periodicity is this whole string, like 14 or something, and that's going to appear to have a periodicity of 8 or 9 repeating. But anyway, that's in principle, if you had a long enough message, you could still break the Vigenere cipher, but you'd have to find correlations to figure out how long the key was, and then take only the characters that were encrypted with the same key value and try to break them. So it'd be much more difficult. And if you think about what we just did, the attack we just did would not work because of Vigenere. Yeah, it sounds about right. Anyway, you won't be able to read it by just decrypting one letter, but you don't really need to read the letter because frequency analysis will do it. In English, the letters are not equally likely at all. In fact, E is far more likely than any other letter, and then T and A are about tied. And that's all you need to know to do this. In fact, E alone is all you need to know. Even a couple of sentences is usually enough that the E's will become very popular. So here's a Caesar program that converts to upper space and preserves spaces. That's the only thing special about this one, so it doesn't get confused by non-alphabetic characters. And now we can encrypt a whole paragraph. So if you run Python 3, Caesar 3, we can feed in a paragraph, and I found a good paragraph here before class. So there's a paragraph. If I give it a shift of, say, 7, it turns into this gibberish. And I can find the key from that gibberish by doing frequency analysis. So if I run the frequency analysis program and feed in that text, it calculates how many times each letter appears, And you can see right here, 50 times L appears, far more than anything else. So the shift is 1, 2, 3, 4, 5, 6, 7. You can just tell by looking at the most popular letter and assuming it's E. And you could get fancy and include information from T and A and so on, but you probably don't really have to. So that's where you can deduce the key from a pattern in the ciphertext. All right. So that's the Caesar cipher. It shows the fundamental principles, and of course that's not good enough, and we need stronger ones, but they're made by variations on that. So you have permutations where you translate one letter to another letter, and that's one component, and the other one is a mode of operation, which is how you handle messages of arbitrary size. Now the Caesar cipher has no problem with the length of the message. It does each letter independently. And here somebody's got a frequency analysis tool. Well, that's good. Okay. Yeah, a bunch of online tools to do all this if you don't want to write your own Python scripts. Absolutely. Anyway, so the permutation should be determined by the key, and different keys should have different permutations, of course, and the permutation should look random. You should not find any patterns in the ciphertext. And this now the Caesar cipher encrypts letters one at a time, and the next letter is just encrypted completely independently. So that means if you have a double letter here, you have a double letter in the ciphertext. So that is bad. This is a dangerous mode of operation called electronic codebook mode, where if you have duplicated input, you get duplicated output, and that's a serious weakness. So there are more secure modes that prevent that. And I mentioned the perfect encryption, of course, is the one-time pad. XOR is the natural way to do it these days with binary. You just have a stream of bits. So if I have message bits here and key bits here, you just combine them with XOR. So if the two bits are the same, you get 0. And if the two bits are different, you get 1. That's all there is to it. Another way to look at it is if this bit is 0, you don't change that one. And if this bit is 1, you do flip that one. They're two equally correct ways to describe it. But the point is you can take a bit stream of plain text and combine it with a bit stream of keys this way. And the good thing about it is it can be reversed if you know the key. So here's the game. If I have a random, pseudo-random key string, and I take ABC and encrypt it, I'll get encrypted stuff. If the key is random and never reused, and it's longer than the whole message, there is no pattern in the output at all. There's no bit that is encrypted the same way as another bit anywhere, so there's no possible way to deduce what happened just by looking at the ciphertext. In fact, if you think about it, if you try to brute force attack with every possible bit stream, you would create every possible output bit stream. So unlike the Caesar cipher, you would have many of them turn into readable text. You would create every possible readable message, and you'd have no way to know which one is correct. And this simple logic has held up for centuries. No one has found any flaw in it. The one-time pad is completely unbreakable. It's just very irritating to use. You have to somehow distribute a key to the other person that is longer than all the messages you're ever going to send and never reuse it. And in practice, that key handling problem is so large that people keep cheating by reusing the key twice or something, and then it doesn't stay secure. But if you can do that, and there are very few cases where people can find a way to do that, then you'd have a really unbreakable cipher. All right. So let's take a look at some Kahoots. And students told me in the last one, I can now display the questions with the Kahoots, which is cool. So these should be somewhat more fun to do. You don't have to wait for the Twitch delay to see the question. So this is 1A, play. And there is a new option that I have to turn on down here. Show questions and answers on players' devices. That's the new option. So Kahoot has improved. I also noticed today that there's a limit of 10 players, and I looked it up. Apparently they got kicked in like 2 years ago, but I guess I'm grandfathered in because I've never had that limit. Yes, you can participate in if you like. There is extra credit if you get the most of these right. It's an online quiz game. You don't have to do it, but if you do get the most right, you get some extra points. It usually helps prevent people falling asleep. Yes, you need to go to kahoot.it and then put in that number, 233-9381. Yep. Yeah, I'm apparently one of the founding members. Well, yeah, I learned about Kahoot from Cyber Patriot, which is a Air Force program to teach security to high school students. I went to a training course for that. They had this Kahoot thing, and I said, that thing is great. I'm going to use that. I used to use something very similar called iClickers, hardware version of the same thing. So I was clearly in the target audience. Yeah, it's got to be kahoot.it. I think kahoot.com won't work, but maybe it does now. I don't know. Oh, yeah, the memes. Yeah, I thought that was fun. There were so many fun memes, especially because of cryptocurrency. Yeah, I'm glad to hear it. All right. Well, I'll wait a few more minutes. Looks like people are still coming in. All right. I think we've got everybody. All right. All right. So which one of these has to be kept secret? The key, right. All the secrecy is in the key. All right. All right. Which one of these is the weakest? All right, Vigenere, right? Something like that. But Caesar is the weakest. Vigenere is in the middle. All right. All right, which one is the most difficult to use? The one-time pad has a serious key distribution problem. All right. And what process allows messages of various sizes to be encrypted? All right, that's called the mode of operation, how you extend it to handle arbitrary length messages. All right, here's the winners. They will have to tell me who they are if they want credit. I know who that is. And I know who that is. Okay, so Woot will not get their points unless they come out of the closet. But the other two, I think, gave me close enough to a real name. Woot, okay. Well, that's still not telling me much. Okay. I'll record the other name, but unless one of these actually resembles a real name, you won't get your points. However, all right. Let's see, it's 6:30. Good, we can just keep going. All right, so you can put it in the chat if you want to. You can put it in Zoom. You can send it in email, I suppose, to where the class emails go if you want to maintain some confidentiality. So you could send a private message. That's possible, although I don't. Yeah, you try that. I see. I got a pile of them. So that's something called whispers. A whole bunch of them. Oh my goodness. Yeah, you can put it there. I'll notice it now. Just I often fail to notice it. Yeah, if you put it there now, I'll find it. Yeah, you can put it in encryption. Yeah. Yeah, you can send something called a whisper, which appears to be a DM. Anyway, all right, so let's talk about encryption security. So if you're going to define the security of an encryption scheme, you have to define the attack model. As in all security, there's no such thing as just plain security. What there is a level of security considering certain types of attacks. It's not like there's one number that determines how secure you are. So this is how you do. You determine whether something is safe or not. You consider various attack models. So here, for example, is the XKCD about it, right? If you use 4096-bit RSA, nobody can ever crack it with trying all possible keys or anything, but there's always another way in. You just drug somebody and hit them with a wrench until they give you the password, and that's the point. If you use modern TLS on the internet, TLS 1.2, or I think it's up to 1.3 now, that's really very good. Nobody's reading that without the key. There's only a few attacks, but they're very difficult. But if I just put a keylogger on your machine and get your key presses before they're encrypted, I get your data. Or if I just hide a camera in your room, or sneak up behind you and watch you type, I can see what you're doing and get the secret information, even though the encrypted stuff is encrypted. So encryption doesn't protect you against all attacks. It forces you to use a different attack. So we have to talk about what attack you're going to use. So here's the fundamental principle, Kerckhoff principle. The key is secret, but the cipher is not secret. This is what most cryptographers say is the safest thing, is to let everybody know how the encryption works so they can test it and try to crack it and improve it, and all secrecy is in the key. And aha, I see a pop-up telling me that there's a message or something. Oh yes, neat, it worked. Yes, okay, thanks. I got your name. Cool. And it actually pops up to make it easy for me to find you, which is very nice. All right. Oh, I see. Good. Good. All right, so the whisper is better than it used to be. It actually pops up so I might notice it. Anyway, so here's various models. A black box is where you do not know anything about the cipher. So all you see is the cipher text, and you're going to try and somehow deduce the message from that. Or you can have known plain text, where you know the plain text and you know the cipher text. This was, by the way, the situation with WEP encryption of wireless traffic, because there's the most common packet on wireless networks is ARP packets, and you can guess almost every bit in an ARP packet. They're pretty much all the same. So you know what those things, the plain text of those things are, so you can look at the encrypted version and you know what the plain text is. Then you can have chosen plain text, where I can actually feed in plain text and it will encrypt it for me and I can see the cipher text. And then chosen cipher text, where I can perform encryption and decryption, and I'm trying to find the key. All right. Then there's gray box models, where you have access to the implementation and you can tamper with the internals. So these are like attacks where you mess with the device doing the encryption, like side channel attacks. You measure something else like the radio emitted by it, or the timing or the power consumption of the device actually doing the encryption. And that's non-invasive. This is, by the way, very deadly, almost impossible to prevent. It depends on the hardware and the algorithm and everything. And then there's invasive attacks, where you actually modify the system doing the encryption by messing with the hardware, breaking the hardware, exposing it to radiation, causing it to make more errors, and then using the errors to deduce something about the key. That's also very powerful, but it depends on what type of hardware you're using. All right, so here's some goals. Indistinguishability should mean the ciphertext just looks random. There's no patterns at all. Non-malleability means you cannot create a different valid ciphertext from the original one. There's no easy transformation that will create a valid ciphertext. If you change anything, it will be rejected by the decryption process as not valid. Indistinguishability against a chosen plaintext attack. This means two identical plaintexts must result in different ciphertexts. That's what we were talking about before as the problem with electronic codebook mode and the Caesar cipher in the simplest case. If you have two inputs that are the same, it has identical outputs. And that means it's not really scrambling all the information out of the input. So this is not good, and the general way you'd fix this is by having a thing called a nonce, which is a random bit added to it before you encrypt it. So asymmetric encryption is really important in the modern world. This is where you have two keys. Everybody has a public key and a private key, and they keep the private key secret, and they publish the public key. Yeah, a salt and a nonce are essentially the same thing. Yeah, exactly. Anyway, we're not going to talk more about this right away. You should mention it for completeness. There is public key encryption, and it'll come later. But all we're doing right now is symmetric encryption, the old-fashioned kind. So you can also want more than encryption. You might want to provide more than simply confidentiality, which is all encryption gives you. You might want identification. Authenticated encryption returns a tag, which means I've basically a signature. I've signed it, so now you can check that the message has not been altered, and you also know who sent it. Yes, salt is a type of nonce. As far as I can tell, a salt and a nonce are the same thing. There might be some mathematical distinction, but in practice they seem to be the same thing. And here's one example, authenticated encryption with associated data. We'll be talking about this is what's actually used quite often because you often would like to sign something in addition to encrypting it. There's format preserving encryption, so you can encrypt things in a database that was designed to run without encryption. So if your database was designed to store IP addresses, you can encrypt them, but they still look like IP addresses. They don't turn into random bits, so they'll fit in the database along with the unencrypted stuff. That's format preserving. There's fully homomorphic encryption, which is pretty much insane. And people are marketing products, but as far as I can tell, they're not really ready for prime time. This is the idea where you would work on data without decrypting it at all. You would search encrypted data without decrypting it, and you would even do operations on encrypted data without decrypting it. Now that sounds impossible. It's not impossible, it's just almost impossible. The math was developed, I think, around 2000 or so, and it is so complicated that it runs really, really slow. But it can, 2009. It can be done. So you can search through data without decrypting it, and the idea is you could do something like authorize someone to look up like how old you are in a medical database, and they would not be able to determine other things like your medical history, even though the data is in there, because your privileges would give them only the right to find that one fact from the encrypted database. They wouldn't have a key that would let them decrypt all the data and see things they aren't supposed to see. That's why a lot of people would like to have this, and there's at least one commercial product in Vail. I heard them advertising a lot a couple of years ago, claiming they can use homomorphic encryption, and therefore you will never decrypt. You will do your math on encrypted data that stays encrypted all the time, which sounds great. In the homework, I added a few projects at the end, I think in the madness section, where you use a few homomorphic encryption implementations, and you will discover it is miserably slow. Like to look through a list of 50 items takes 5 minutes. So various people argue with me and say there is a new version that's better. And I say, boy, I hope so, because the versions I found are not even remotely ready for practical use yet. Yeah, of course, if this would really work fast enough to be used, that would be pretty awesome. It protects your privacy in a lot of ways. So there's a lot of interest in it. But I don't really think it's fast enough yet. And then there's tweakable encryption. For example, if you're encrypting every block on a hard drive, you want to scramble each block differently, and yet you don't want to make the data any bigger because that would be hard to implement. So you use something like a tweak parameter, which is again like a nonce or an initialization vector, an extra bit added to each bit to mean that two identical blocks come out different. All right, and so here's things that can go wrong. Yeah. So you can have a weak cipher, for example. You've seen, by the way, one thing, the key space can be too small, like the Caesar cipher. And that's what was ultimately wrong with DES. The key space was too small, so you could just try every possible key. Another thing is you can make it so it's vulnerable to a time-memory trade-off where you can make a lookup table to make it possible to perform encryption operations really fast, so then you can try a lot of keys and break in. And the padding oracle is another one. You did not really, the situation here is people used encryption for authentication, which it was not designed for. And this is the kind of problem that I see a lot. People use the wrong kind of encryption because they don't actually understand what the encryption is doing. So they would have the administrative user send encrypted data, and if it decrypted at the other end, they would interpret that as proof that you were the administrator. So if I could just send any valid ciphertext, it would believe me that that was authentication as well. And the problem is the server provided error messages which gave you more information than was necessary. They would tell you if there was a padding problem or if it was a different problem with the encryption, and therefore by watching those padding errors, you could carefully craft, after a few guesses, you could carefully craft a encrypted message that was valid and appear to be the administrator. And we'll do this in the attack. That's the padding oracle attack. There are two fundamental problems. One is that the fact that you encrypted something is taken as proof of your identity, which is not really what it's supposed to do. And the second problem is an overly informative error message. Instead of just telling you input rejected, it would tell you more information about why it was rejected, and that turned out to be information that you could use to attack it. All right, so let's try another Kahoot, which is 1B. And make sure I've turned on this thing. That's good. Okay. Okay. All right, I'll give it a few more seconds. I think there were 17 before, but we may have had 2 people fall asleep. Maybe not, though. Boy, Frack, that's a magazine that's hard to read. Boy, a lot of good stuff in there, but it's really advanced. I've never been able to understand more than about 1/10 to 1/4 of the articles in Frack. All right. All right, so what is required for users to know whether a cipher is safe to use? Okay, you need to have modeling. If people ask you whether something is safe, you have to have a threat model. You have to understand what the risks are. All right, what includes COA and KPA? Okay. Okay. That's a little tough. Okay, those are black box models, known plain text and ciphertext only attacks. This is probably the simplest one you always think about. Somebody reads the encrypted stuff off the wire and that's all they get. Like my email, I encrypt email or web traffic, I send it off, and the simple thing I always think is somebody is picking up that traffic like at a router. Can they read it? All they have is the ciphertext. That's probably the most common attack. All right. All right, what category includes lowering the power supply? This was used to crack RSA about 10 years ago. Yeah, that's an invasive attack where you modify the operation. All right. You lower the power supply and then it makes more errors, and the errors have a non-random effect on the output, and you can deduce something about the key from them. All right, what about side channel attacks? Yeah, I think they call that a gray box model, where you have some visibility into the hardware. All right. All right. I know who that is. All right, and that might be close enough to a real name. I'm not sure. My long-suffering grader is good at figuring it out. And that looks close enough to a real name. All right. So I'm going to stop recording.